He even knows who he is. I didn't have to cue him. He likes that role. Is there any well, let's wait till everybody's on. So, dear henchman, is assignment number 3 getting warmed up in the oven?
Yep, I will release it this weekend.
All righty. You guys know what's coming.
Is winter coming?
Winter
Winter
may be
comes at
coming.
around, I'd say, assignment number of all of the ones that are the hardest. This one potentially is harder. So that Brian has gone through this. Brian, what's the hardest?
I think this one was the hardest for me.
Well, that's a good motivator. Get it over with, and then it's easy street after this. Well, let's begin. So I'd like to review just finally the material behavior stuff, go through a little bit of the extensions to the more fancy material laws, which will be really the subject of assignment number 3, as we'll start out with linear elasticity, which I think I've given you a reasonably good foundation for. But what comes next is, of course, how to use it for an industrial material. And many of you that may end up going to work in industry or national labs or things like this, you'll encounter these kinds of constitutive laws all the time because they're useful for things like metal forming or composite materials or thermoformed materials. So they're very useful, but again, it's not the subject of this class is to go after material laws. So I'll just simply show you a couple, but there are many that are out there in the literature. So where we left off is we have, the first law of thermodynamics tells us that in the linear elastic regime, we basically have something that looks like this, and we can write this in many different forms. This is linearized elasticity, and of course, infinitesimal deformations. So many assumptions, and the primary reason is that, the strain is a small strain, and the stress is the Cauchy stress, and this, of course, is the elasticity tensor. Now, the problem with that, we just switch glasses. Here. So the problem with this, of course, is it's infinitesimally small. So the tendency is to at first think, well, maybe I can apply it to all kinds of other deformation regimes. And that is a classical mistake that people make. And so clearly the problem is that neither this nor this are going to be compatible with finite deformations. There's something called the principle of material frame indifference. And if you're interested in sort of the theoretical reasoning behind constitutive laws in general, it's important to think about taking potentially a more advanced class. That advanced class in this case would be MEC 185, and sometimes it goes by the graduate version called 287. That's offered every fall semester in the department, and it's definitely a worthwhile class to take, but it'd be especially useful, I think, after you've taken already this class, because then you'll see more of the theoretical underpinnings, which are not the subject of this class, but anyway, are somewhat important. So in the special case of linearized elasticity that is now isotropic, so of course, if it's isotropic, now we have two material constants, kappa or mu, Poisson ratio or Young's modulus, and there are a couple of other ones, for example, sometimes referred to as the Lamé parameters. They're not as widely used pretty much because these have the most physical meaning. So we went through all of that business of going through when a material is isotropic. The elasticity tensor, as we know here, and I'm not going to rewrite it because we're already just going through a review, has just simply two entries here that are that can replicate every single one of the the parameters inside the elasticity tensor. So normally each one of these things is labeled E111, E1122, etc. And it turns out that each of those parameters can be represented as some combination of mu and kappa. In this case, on the diagonal, it's kappa plus 4/3 mu, and then off diagonal is kappa 2/3 mu, and then over here, mu, mu, mu. And of course, the eigenvalues of E are important because they have to be positive definite. So those things are 3 kappa, 2 mu, 2 mu, 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 and mu. And of course, those have to be always positive, and of course, also less than infinity. So that has very physical reasoning that it's not difficult to understand why. So finally, at this point, when we write the constitutive law, there's a compact way of writing it. We can write it as 3 kappa times the trace of epsilon divided by 3 multiplied times the identity plus 2 mu times epsilon prime. And the decomposition is, of course, useful. This is the volumetric part of the deformation or volumetric part of the stress, and this is the deviatoric part. Now, that becomes useful because later when we start to consider constitutive laws and failure, we'll see that the failure theories, in fact, are going to home in on exactly this component of the constitutive law. In other words, the failure laws, which we got to last time in class at the very end, basically focus on one thing. They focus on the magnitude of how big that deviatoric stress is. So the deviatoric stress, just as a recap, is this thing right there. And the deviatoric stress's magnitude, we get that by taking the inner product of the stress with itself and then taking the square root. And if we do that, we find out that this is equal to 2/3 sigma 0 squared divided by 1/2. And of course, that is, raised to the 1/2 power. And that parameter then is the failure parameter that is usually considered to be the yield stress in theories of plasticity.
Excuse me, Professor.
Yes.
There's just the slimmest portion of your notebook that's a little bit
Oh,
cut off.
sure. Let me get that for you. Just a second. It's hard for me to see there.
Beautiful.
That better?
Yes, much.
Okay, super. Okay, so in general, what we have is we have the parameters then that sigma 0, and depending upon the type of testing law, we basically have this constitutive law that or this kind of failure criteria that occurs when you do this, when you extract the parameter from a uniaxial test. So this parameter is the parameter that is associated with the test of uniaxial tension. We also have another possible test, and the other possible test is if we take a piece of material, we shear it in 2 different directions with tau 0, and basically from there, what we find out is the magnitude of sigma prime with itself is equal to, in this case, 2 times tau 0 squared. So in one case, it is sigma prime inner product with sigma prime 2/3 sigma 0 squared. That's from the uniaxial tension case. And then from the shear type test, it could be this. Now there could be conceivably others, but the common theme here is that it's the magnitude of how big the deviatoric stress is considered the first possible angle of attack to go after describing some kind of nonlinear behavior. Okay, so that's where we left off. And of course, what I want to do now is to basically extend these kinds of laws to see exactly what are those kinds of constitutive laws that go into the finite regime. So one very popular one that you see on screen is the so-called Kirchhoff-Saint Venant law. And that one basically starts with the following argument. It goes from, again, from the first law of thermodynamics. But it says, you know what, we're going to stick with this thing being finite deformation. So this is not equal to sigma multiplied times epsilon prime. We're going to retain these finite deformation variables. And if you go through the algebra here, and I don't want to go through that today, I mean, it's relatively straightforward. What you find out is that the implication of this is that S must be equal to E, the same E that we have in linearized elasticity, but multiplied times the Green-Legrand strain. So there's 2 things that are different about this law. You have the second Piola-Kirchhoff stress instead of the Cauchy stress. You have the Green-Legrand strain and its time derivative, by the way, instead of the deformation variable being the strain deformation here. So this turns out to be, this constitutive law, probably the most commonly used, for example, in aircraft industry, cars, plates and shells, any kind of deformation where the deformations are just slightly bigger than 1 or 2%. People switch usually from the constitutive law that has to do with Hooke's law, which is shown here, and they replace it with this law. Now, the first thing you'd say, well, it looks almost exactly the same. That doesn't look very nonlinear to me. It's linear in weirdo variables. The problem is that this thing is an artificial fake variable. It doesn't have any physical meaning. So when we convert it back into Cauchy stress, we're going to see that this constitutive law has all kinds of strange behavior about it. E is also nonlinear because it's not linear in terms of the displacement. So let's go through the exercise of what that really looks like. So the stress is equal to 1 over J Fs Ft. Okay, that's what we had before from almost 2 weeks ago. And if I replace that then, and I replace the S here in there, what I end up getting is that this constitutive law looks quite a bit different than any kind of normal material behavior. So what I find out is if I take sigma, I multiply it times J, I multiply it times F inverse, I multiply it by F inverse transpose, I can isolate what S is. So if I put this S back into here, into this constitutive law here, what I see is it's highly nonlinear. So it basically looks like something like this. It's F inverse multiplied times sigma multiplied times F transpose. J is a scalar, so we can bring it outside of here. It looks like that. And then this is equal to, in this case, E, the elasticity tensor, multiplied times 1/2 F transpose dotted with F, because that's, of course, what the Green-Legrand strain is, minus 1. So this law is anything but linear. When you start to look at it, it has a very weird behavior or relationship between sigma and also F. So this constitutive law, while the first law of thermodynamics dictates that's what it has to look like, so it isn't an option for us. We come to the first law of thermodynamics, and by the same arguments, we find out that this has to be the constitutive law in the very small but moderately large deformation. So it doesn't have to necessarily be infinitesimally small. This extends the ideas. But what we find out is that this constitutive law now takes the place of Hooke's law. Now, it turns out in the limit, as the F gets closer and closer to 1, so in other words, the deformations become infinitesimally small, this goes bye-bye, this goes bye-bye, this goes bye-bye, and this ends up turning out to be epsilon. So this will recapture sigma is equal to E multiplied times epsilon. So it's the go-to constitutive law that's very useful in industry when people want to extend simple linear elastic laws to moderate strains. So moderate strains might be 5, maybe 10% strains. So basically things that are pretty big, that are noticeably big, this is the constitutive law that people use. And this is sometimes called the Kirchhoff-Saint Venant constitutive law. And you'll see this in many finite element packages and all kinds of other literature. It's widely used. So that's the first one. The second kind of extension to this, unfortunately, this constitutive law that looks like this, which is E multiplied times E, is still elastic. That's the problem. In other words, it's moderate strain, but it still has elastic behavior. So what we have to do is we have to actually extend this thing to nonlinear behavior. And this is what is the subject or the theme of assignment number 3. We're going to guide you through how you do this for an industrial type of problem where you include all kinds of interesting effects such as plasticity, damage, thermoelastic strain, and so forth. So the typical way this is done, so these are sometimes called industrial constitutive laws. So basically widely used in a lot of different industries. And what they say is the following: we still take S, we set this equal to, again, your E, just like before, multiplied by E, but we're going to add all kinds of features to this. The first feature is going to be, we're going to have a variable that's called alpha, and alpha is sometimes referred to as the damage variable. It lives between 1 and 0. If alpha, and we put a 0 here to indicate this is the undamaged material before any type of effects have occurred. If alpha is equal to 1, it recaptures exactly the elasticity. If alpha becomes 0, it means that there's no more stiffness in the material law. So let's see what physically what that means. For example, if I take a piece of material and I pull on it, and I keep pulling on it more and more and more, if I look at the microscope and see what's going on, depending upon the type of material, it's going to start to develop little cracks as the material starts to evolve. It's also going to develop little voids, cavitation, all kinds of other stuff. And that is going to disturb the integrity of the material. So this material might have initially the stiffness E0, but after it goes through this motion or deformation of being pulled apart, the first easiest way to describe this is to simply say, well, whatever the material law is, we're now going to simply reduce it by the amount of cracks that exist in the material. So sometimes what is done is they correlate this alpha with the so-called crack density of a piece of material. So what that means is, as the number of cracks start to increase more and more and more, and as you can see from here, more and more and more, eventually what happens is the cracks start to get to such a critical density that they start to connect and the material simply breaks apart. And of course, then the material has 0 stiffness. So the idea is we account for all of that stuff, which is not easy to accommodate or account for in a very, very detailed way. But a macroscopic way of doing this is just simply to multiply E by a parameter. So this thing is sometimes referred to as a damage parameter. Damage parameter. It's widely used, for example, in concrete, glass, materials that are brittle and don't have any ability to plastify in any way. People use these so-called damage laws to calculate or to keep track of how much of the material is being damaged. Now, at the same time, there are other effects that we might want to take into account. For example, one in particular is the so-called plastic strain of the material. And the plastic strain of the material is also an effect that is phenomenological. And basically what happens is whenever we pull on a piece of material, again, pulling on a piece of material here, and we keep pulling on it, if it happens to be a material that admits itself to having some type of plasticity, meaning some type of permanent deformation that stays with the material after I leave the stresses or hands off of the stresses, we account for that usually with the model that looks like this. We usually take the strain versus stress. And when the material starts to plastify and we let it go, it comes back down to some effect here. And this amount here is usually referred to as the plastic strain. Okay, so the models for this are somewhat complicated because this is not an easy thing to put into a constitutive law, because as we pull on the piece of material and then let it go, if we pull on it again, it starts from here and then it let it go and it comes back here. And so you start to have this weird ratcheting behavior where every time you deform the material, it starts out from a new permanent deformation state. So if I pulled on this material and I stretched it, and then I let it go, it would stretch back down to probably this size, but it wouldn't be the same size that it originally was. It'll be a little bit bigger. That amount is in fact exactly equal to this plastic strain. Now, the way we account for this is we take the total strain, this is the Green-Legrand strain, and we add this different parameter here, epsilon plastic. Now, the first important thing to understand is there's a minus sign here. Most people want to immediately say, well, we're going to add some plasticity. There's got to be a plus here. Part of the exercise of what I want you to do in the assignment is to understand it. In fact, this is a minus sign, and there's some certain arguments that Brian hopefully will go through in the help session when he starts to socialize this problem. But it is an effect that basically requires a minus sign here. Now, There is another effect in addition to this that is the so-called thermoelastic strain. And that one we know a little bit more about because of our undergraduate days. We usually have some connection to thermoelastic strains. Let me rewrite that here on the next page. So this is alpha times E0 multiplied times E, sorry, 2 lines, minus EP minus E theta, which is the thermal strain. The thermal strain is typically given by the following type of argument. If you take a rod of some kind of a material and you heat it up, so you put a flame underneath, so I'll draw it with a candle, I heat up the piece of material, and the material then starts to expand by a certain amount. Well, the amount that it expands is typically given by something called the thermoelastic coefficient. And the thermoelastic coefficient basically says the following. Take this coefficient, which is usually measured for a thin piece of material, multiply it times the temperature difference, and project it onto the diagonal. So what this term looks like, it looks like something like this. It's basically beta times theta minus theta 0, beta times theta minus theta 0, beta times theta minus theta 0, 0, 0, 0, 0, 0, 0, where beta is the thermal expansion coefficient. This is the reference temperature where there's no deformation at all. So that's usually absolute 0 or some reference measurement. And this is the current temperature. So what that means is that beta, of course, is a positive parameter. It's greater than 0. So what this states is that a piece of material is going to have strains in all 3 directions. When it gets heated up, the material is going to expand to a self-similar cube. Now, there's some assumptions here. The first assumption is that the material stretches or grows in all 3 directions the same way. Well, the implicit assumption here first is this is isotropic, okay? Because if it was anisotropic, we would have different coefficients beta in each of these 3 directions. In other words, there would be a beta 1, a beta 2, a beta 3. Number 2, what it also states is that the temperature, if it's increasing beyond this state, is going to have some growth, and it's going to have growth in all of the 3 directions. And if it's less than that, it's going to have shrinkage where the material will start to shrink below that value, like so. So that's usually, again, the simplest model in a whole family of models for thermoelastic strains. And as you'll see in the assignment that Brian will mail out to you, I explain all of this in the notes. And I want you to go through the theory, understand exactly what these extensions are, and then implement those extensions in a problem where we're going to take essentially a raw piece of material. So we'll talk about that more next week after you've had time to take a look at it. We're going to take a raw piece of material, so some raw ore that someone mines from somewhere, and we're going to take a compressive plunger. We're going to squish the material so that it now looks something like this, where the material is being squished, and we're going to pump electricity through it at the same time so that we can heat up the material and make it soft and compliant. Okay, so wait till Brian sends out the assignment. We'll talk about it next week. But this requires us to do a little bit more work on exactly how we integrate constitutive laws, how we understand how material laws evolve. And so we'll talk about that when the assignment comes out. But the essential key parts to explain how that works are page 12 and 13 in the last packet, packet number 8, which basically shows you how you compute how these damage variables evolve, how you make plastic variables evolve, and how you compute, for example, thermoelastic stresses. Okay, it's a really great problem. It was a problem that was given to me many, many years ago by the company Siemens, where they wanted to make thermal barrier coatings for turbine blades. And they were compacting materials that were extremely non-compliant, basically yttrium, which is a thermal barrier coating. And they ran a huge electric fields to melt the material and at the same time to compress it to get all of the little pores out. So it definitely is a good problem to sink your teeth into, and I think it's quite a good one. So Brian, is there anything you want to add about that assignment before I get into the review part? Brian? I will assume Brian has nothing to add right now, but so we'll come back to him later. So we finished pretty much 6 weeks of a lot of stuff. First week was robots, then genetic algorithms and machine learning. Then we did stress, then deformation, then stress, then constitutive laws, which is now what we're finished with. And so our final frontier is to think about electromagnetism. But I thought before we jump into that, meaty topic, because it is definitely a not easy topic, but a very important one, let's go through the review of exactly what we've seen. So before I do that, I'm happy to take any questions, but if not, I'll dive right into the review. All right, then let me get going here. So important points. So this is critical for you to understand for the next couple of weeks. We will use all of these things to solve some industrial type of problems. So first 5 weeks. The first thing is you need to feel comfortable with computing this kind of a creature, okay? So that is the divergence of the stress. What that really means is it's the partial of sigma ij with respect to xj, summation of j equals 1 to 3. I would feel comfortable understanding what that divergence means. So if I gave you, for example, a stress, and I told you compute its divergence, you need to be able to show me that you can compute this kind of a quantity. Okay, now that's important because it requires us to do 3 actual calculations here. If we look at exactly what's going on, what happens is that sigma in this case is what? So if you look at sigma ij, and we take the partial with respect to xj, and we pick, for example, j equals to 1, what that means, or sorry, I equals to 1, what that means is this is the partial of sigma 1 with respect to x1 plus sigma 1, 2 with respect to x2 plus sigma 1, 3 with respect to x3, okay? When I is equal to 2, this is the partial of sigma 2, 1 with respect to x1 plus the partial of sigma 2, 2 with respect to x2 plus the partial of sigma 2, 3 with respect to x3. Then I equals to 3 is the partial of sigma 3, 1 with respect to x1 plus this partial of sigma 3, 2 with respect to x2 plus the partial of sigma 3, 3 with respect to x3. The main message here is there are 3 partial differential equations hiding inside of divergence of sigma. Divergence of sigma really means all this junk that's here. So you have to be careful with being able to unpack these things to understand exactly the implications of that pretty compact notation. Now, we use this, of course, in one specific case. Whenever we take the divergence of sigma plus the body loads is equal to rho v dot, that in fact gives us the fact that all of the differential equations that are shown here, these are 3 of them there. This thing here is F1, F2, and F3 because there's 3 body loads. And this thing is rho times the partial of v, or sorry, the derivative of v with respect to t for the first component, the derivative of v with respect to the second component, the derivative of v with respect to dt for the third component. So hiding inside of this innocent one little equation is a lot of junk. You should feel comfortable with that. You probably have seen all of this already before as undergraduates when dealing in fluid mechanics and probably sometime in mechanics, but nonetheless, this would be good to know. Number 2, the idea of the stress dotted with the normal that equals the traction vector, that's extremely important. And really what that allows you to do is that if you come to a body and you say, right at this point, I want to know how big the traction or the forces per unit area are right at this location on this surface So for example, perhaps I'm putting a strain gauge or some kind of thing at this location here. How you do that is you compute the stress that is at that location. So that's the little stress box, and you multiply that stress by the normal that is shown there. All of that product gives you the traction vector. Now, that's really important if you're an experimentalist, because if you're an experimentalist, what you're going to really measure are things on the surface of the material. So you're going to usually always measure things like the traction. You know already what the normal is. The normal doesn't necessarily always fall directly in the same direction of the traction, but it allows you then to take the stress, which is hiding underneath here, and correlate it with what you actually see on the surface. Those are very valuable techniques when people want to do non-destructive testing or want to do surface measurements of materials to see if there's cracks underneath. It's very important to have a good feel for exactly what sigma dot n is. Okay, the third important point is that if we take the stress and we take its inner product with the gradient of V, the stress with the inner product with the gradient of V really means that I take the matrix sigma 1, 1, 1, 2, etc., 3 by 3 matrix. I multiply this times the partial of V with respect to x1, partial of V1 with respect to x2, and so forth. That's also a 3 by 3 matrix. And then I proceed to multiply this times this times this, add them all up, and that gives me a scalar that is the so-called stress power. So this is the stress power. And it, of course, appears in a very important equation to us, the first law of thermodynamics, which states that the density multiplied times the stored energy per unit mass is equal to the stress power, this guy right here, times the gradient of V minus the divergence of Q plus the mass density multiplied times the number of sources, or the sources of the material that are being added to the material. And of course, this could be lasers and other stuff, and it will be when we start to get to that. So bottom line is, you need to feel comfortable with how you compute these second order or double contractions. And I know through Brian that many of you have felt uncomfortable with this. So again, the double contraction when things are matrices are just simply products of everything in each matrix added up together. Any questions about that?
So the two matrices in the top right-hand corner, it's like we're taking a dot product between them, except it's a matrix, not a vector.
That is correct. So basically, if I were to write out all three of these, there's 3 entries here on each row. And there's 3 entries here. Let me just call them O's. So X's and O's. And I'm going to take this X times this O, this X times this O, and I'm going to add them all up. That summation of all of those is exactly the double dot between matrix A and matrix B. So this would be A, this would be B.
And we're going to keep each row to itself. So we're going to end up with a column vector, right?
Well, I mean, actually, you end up getting a scalar here.
Oh, okay.
So what happens is you multiply this times this and add it to this times this, 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 this times this 9 times. You actually don't leave it as a row or a column. You add them all up, multiply times their corresponding entries here, and it gives you a scalar at the end.
Sometimes there will be,
1 dot.
or there will be a matrix, colon, matrix, colon, matrix.
Okay,
So we have to do it twice. So how does
matrix, colon, matrix, colon, oh, I see. So what you're saying. Okay.
that? Yeah.
So let me give you a tangible example of that. So this is, for example, when we take the stored energy in the body, it's 1/2 epsilon, inner product with E, inner product with epsilon. Really what that means is this is the 1/2 summation of first, the summation of KL, EI, JKL, epsilon KL. Okay, so we multiply all of these things and we multiply them, add them together. Then we multiply all of this times epsilon IJ, which is the remainder of what's here. and all of that stuff becomes a scalar. In fact, let me go to the notes to show you the more neater version of this. It's shown here in the notes. That double contraction is exactly this quantity that appears here. So 4 things are being multiplied. This times this, these are 2. So that's the first entries that are associated with those summations. And then the product of all of that stuff is none other than the stress, which is sigma ij. So sigma ij multiplied times epsilon ij, let me write that out. Epsilon ij, sigma ij is taken care of by the last 2 summations that are here. And you end up getting a scalar which has no direction or anything and no free indices. The one thing, Lena, you can always sort of try to determine whether something is a scalar or not is ask yourself if it has any indices at all. So for example, temperature doesn't have an index because it's not a vector, so it's a scalar, or concentration, or voltage, things like that don't have any directionality to them. So even though the calculations may be very complicated as they are here, at the end, when they're all added up together, these things all add up to be a single thing, which is the stored energy in the body, which is a scalar. So this would be, of course, in the case of, using metric units, this would be joules.
Okay, great. So because the Green-Lagrange strain has 4 indices.
That's
the
correct.
The stress will still be a matrix.
That
and
is
then we can have
correct.
Okay.
That is
thank you.
exactly right. You got it. That's exactly the right observation. All right, well, let's see. So the next thing we had to review is if we look at the constitutive laws here, we've done the stress, we've done the traction vector, but we also have the idea that in many cases, it's not easy when we start to consider the deformations of the body to consider the deformed configuration where the body might have gone through some crazy deformations like this. So oftentimes what people did is they mapped it back to the reference configuration and rewrote the differential equation that lives here, which is the divergence of sigma plus f equals to rho v dot. And they simply rewrote it as a differential equation. And it ends up, after doing a lot of the transformations, it's the divergence of f dotted with s plus f multiplied times the Jacobian is equal to rho 0 v dot. So that's a very useful tool because what that allows us to do is it allows us to use one configuration or the other depending upon what might be easier in the analysis. And by the same token, the differential equations that live over here for the first law of thermodynamics are rho w dot equals to sigma inner product with gradient of v minus the divergence of q plus rho z. And then over here at this side, the analog to this is rho 0 w dot equals to s inner product with e dot minus the divergence of q0 plus rho 0 times z. So again, that constitutive or that differential equation lives at every point here in the undeformed configuration, and the other one lives in every point here in the deformed configuration. So in some of the stuff that you see in your assignments, we try to give you kind of a feel for using one or the other, but that's also, something that I think is an important highlight. At that point, we then went into the whole idea of constitutive laws, and the constitutive law that we needed to start out with is the so-called linearized elasticity. And linearized elasticity basically starts like this, but this thing is, of course, potentially fully anisotropic. So through several arguments, we find out that if the material is isotropic, meaning that if I pull on it in all the different directions, things simplify. And in fact, we're left with a constitutive law where the elasticity tensor has only 2 parameters that enter into it, kappa and mu, and combinations of those are able to construct every one of the parameters here that appear in the elasticity tensor. So we've just gone through all of that, so there's no reason to rehash it. But I think that this packet number 11 gives you all of the key components of exactly what I think are important for the next 5 or for the last 5 weeks. Now, what's also important, of course, is we go through the ideas of calibration of failure. We went through the 2 different tests, axial tension, and then one on shearing. And then we also just went through just now also the idea of how do you extend the constitutive laws to consider more exotic behavior. Now, what we didn't do due diligence on is that, we still have these weird terms of, in the first law of thermodynamics that have to do with input of energy from some external sources. Now, that's of prime importance to us because the external sources in many cases are going to be, if we have a body, we're going to zap it with a laser and we're going to start to heat up the material in the target zone. Now, the way to account for this is to first go to the fundamental principles of exactly what is optical energy of materials. I mean, what is an optical energy even of a laser? And this is intimately connected to the so-called Maxwell's equations. And Maxwell's equations are the subject of packet number 9, which is in depth, and we're going to go through a little bit of it today. But basically, in many cases, we have 2 possibilities of things we find important from electromagnetic energy. Number 1, we have source terms that look like this, which is something that is a thermal expansion, absorption coefficient. So I'll just draw it like this. I'll put a dash on top of it just to indicate that this is not the damage variable. It's some kind of a variable alpha. So it's a number. And this is the so-called absorption coefficient. And an absorption coefficient is multiplied times the current that is flowing through the material, multiplied times the electric field, which is given by E. We're going to derive that and see where that comes from. But this is basically the term that appears in the first law of thermodynamics, shown here, right? And this is due to electrical flow through a material. Now, what that means is if I take a wire and I pump electricity through it, for example, the current, so I'm using the symbol J, as the material is, or the electricity is flowing through, the electrons, of course, are going to bump up against pieces of the material as they move through the solid, and that's going to generate heat. Now, the amount of heat is controlled by the amount of heat that can actually be absorbed by the material. So depending upon whether the material is a superconducting material or something with low losses, you're going to have a parameter here that's going to account for that, and that is the absorption constant. And we're going to look at that shortly. So the point of this is we have usually either electrical flow, that's a very common thing that we would like to take into account, but then also lasers. So lasers are basically also electric fields. In fact, ironically, it's going to be when we look at a piece of material or a piece of electromagnetic energy, we usually have something that is called the electric field. We have something that's called the magnetic field, H. And if we take the product of E cross with H, because it's a vector that is crossed into there, we have something that comes out here that we usually call the pointing vector. It's not because it's pointing in that direction, it's someone's name. So pointing vector basically tells us where the flow of radiant energy is. So for example, the rays of the sun, that is in fact none other than the pointing vector. The rays of a laser, that's also none other than the pointing vector. So when we take the magnitude of the pointing vector and take its magnitude, we get then, of course, none other than watts. And that's in fact exactly what comes out of a laser that heats the piece of material. So for us to feel comfortable with these 2 big items, because they're 2 big ticket items in manufacturing, because we laser everything, we run electricity through everything, we need to have just a brief introduction to Maxwell's equations. So Maxwell's equations are tough. Normally, if you were going to have a class and you really wanted to master Maxwell's equations, it would be an entire class on electromagnetism. And certainly We don't have the time to do that in this class because it's not the objective, but there are very nice classes in the electrical engineering department. I believe it's EECS 110, and there's also a graduate version of this. But I'm going to try to give you today just a brief overview of it, and we'll polish off anything more on Tuesday. I'll give you a little bit of time to digest this. So the basic ideas of electromagnetism are twofold. So let's take a look here. Okay, so electromagnetism. So again, this is packet number 9, and it's also chapter, if you want to read upon, and I would like you to please read before next class period, chapter number 6. It gives you everything you ever wanted to know, but were afraid to ask about electromagnetism. And it is, I can assure you, a horrifically complex topic. It's horrifically complex enough that people are still winning Nobel Prizes investigating all of the theories of electromagnetism, because it is still somewhat mysterious after almost 150 years of people beating that problem to death. It's still not solved. So Maxwell's equations and magnetism are still very much on the forefront of science. For engineering purposes, there are somewhat phenomenological approaches to this, and that's what we'll mainly discuss today. But if you really want to get into it, for example, things like quantum confinement, quantum mechanics, and things of that sort, you really have to take this to the next level, in particular, also relativistic Maxwell's equations. And it's a beautiful topic, but a little bit outside of what we want to do. But many classes at Berkeley that are on this, considering that many of the people that are actually winning the Nobel Prizes in physics are actually here at UC Berkeley. So this is a topic that people really care about. Anyway, the main issue in electromagnetism and how it first started is that when someone looks at a small charged piece of material, so let's imagine this thing is so small that it's just simply a little isolated point mass, okay? So this little point mass, it has a charge, and the charge is in coulombs. So I'm going to call this thing particle number I, and it has a charge, and that's going to be our essential unit, and this essential unit is going to be in coulombs, okay? So we'll use the symbol here, C, okay? Now, if I were to take an imaginary string, little piece of string, and in fact, that was exactly what people did in the beginning, and I attach it to this charged piece of material, and I flip on the electric field nearby and the magnetic field nearby. So the magnetic field is usually given by Tesla. So of course, this is Tesla, which we all know and love, and this is newtons per coulomb, as we'll see in a few moments, that the amount of force that is exhibited by the string that is resisting this piece of material moving is given by the following relationship. It's equal to F is equal to how much the charge is of the piece of material times the electric field that that piece of material is experiencing, plus the charge of the material times how fast the piece of material is moving, crossed with the magnetic field BI. Now, it took a long time for people to figure out that somewhat elegantly beautiful little relationship. And what it says is the following. It says that the amount of force is directly proportional to how big the electric field is times Q. So you can immediately see what the units are of the electric field. The force that's acting on here, since this has got to be in newtons, right? So this is newtons, that the electric field is this mysterious thing that is equal to newtons divided by coulombs. Now, you don't see electric fields. I mean, unless you do some kind of high-speed photography or you see lightning or things of that sort. The electric fields that are around our laptops, our devices, and things like that of low intensity that are not burning through the atmosphere, because that's the reason you see lightning and things of that sort, are basically, you know, an invisible force. So it is a somewhat artificial force that simply says, look, I have something called the charge. I can measure the force. And if I divide the force by whatever the charge was, this thing that comes out is the so-called electric field. We never actually see it. We just measure it by inference. The inference is basically, I measured a force that was acting on this blob of material, and the magnitude of that force divided by the force divided by this charge tells me how big this electric field is. So that's one thing. Then the second thing is that many experiments, first started, of course, by Faraday, was that this measurement became different. So in other words, measuring this kind of a force that's acting on this piece of material was different when the piece of material was moving around. So what he found out is that if he did a measurement of this force and he took the charge of the piece of material and he made it move around, but at the same time, he induced a magnetic field. So he put a magnet nearby. What he found was that the force was proportional to the charge that the material had. It's how fast it was moving, but cross product with B. That produces pretty weird effects. I have to tell you that, I mean, if you think about how a charged piece of material moves around and it has some kind of a velocity, and you have a magnetic field here, where it's sitting there and it enters into the magnetic field, what will end up happening is that particle will enter the magnetic field and then start to move around in an insane spiral. Now, that's because what happens is when you take the product of V, which is moving in this direction, and the product of B, so depending upon what direction your magnetic field is in, for example, let's suppose it's in this direction, then V cross B ends up being in this direction, perpendicular to both of those. So this particle is going to be moving like this, and then suddenly, whoop, it's going to do a U-turn and move around. But as it does a U-turn, the magnetic field is still there, and it's going to push it around again. And so what ends up happening is this thing makes lots of little U-turns and starts making a circle. Now, that's important enough to win a Nobel Prize for. In fact, that's why we have somebody called Lawrence. So Lawrence Livermore, Lawrence Berkeley, Lawrence everything, that is our illustrious former colleague, Professor Lawrence. And Professor Lawrence basically, discovered this kind of an effect. And this effect was very useful because when he started to think about how you could harness this basic thing that Faraday had discovered, was that you could shoot particles into a track. And if you put a magnetic field, coils all the way around this track, you could spin the particles around the track indefinitely. They would just keep spinning around and around and around and around. And if you kept the magnetic field pretty big, you could really start to speed up that rascal until it got really close to the speed of light. Now, as we know from relativity, as particles become closer and closer to the speed of light, they become infinitely heavy. So that's, at least if we're to believe, relativistic mechanics, and so far we have no reason to disbelieve it. Basically, as the particle starts to get closer and closer to the speed of light, it becomes effectively heavier and heavier. So the idea is that if the mass of the particle times its velocity, which is the acceleration, is equal to the force that's acting on it, and the force is Qi, and then we have, of course, the electric field plus the velocity of the particle times the magnetic field, we start to see that this and this are related. And in fact, the equations for this, depending upon how big the magnetic field is, it's going to start accelerating. So if you start to put a monster magnetic field here, you can start to make this, thing really start to speed up. Well, this is exactly what LBNL does day in and day out. If you ever wonder what all those big giant buildings are up at the hill, they are cyclotrons. And this gadget is, of course, a cyclotron. Now, it's a pretty small scale cyclotron as cyclotrons go. The gigantic one, of course, we all know well, is at CERN. And it's, of course, the Hadron Large Super Collider. So Hadron Large Super Collider, HLSC, which basically speeds up particles as close as possible to the speed of light as possible. They usually have two big giant tracks where the material basically will have one particle that enters here. So I'll draw this particle as one coming here. And at the same time, they put another one in a track here. And as these two things are spinning around on their respective tracks, at some point, they open up the gate and they let the particles interact with each other, and something big and nasty occurs. That's what was the so-called God particle or Higgs boson that had been discovered or had been predicted almost 40 years before by Higgs, and was considered to be either a mathematical artifact or some figment of the differential equations. It turned out they were actually able to measure the Higgs bosons. And in fact, he won then the Nobel Prize after waiting for almost 45 years. So all of that stems from the basics of electromagnetism. So I don't want to clobber you with electromagnetism today completely. So what I would like you to do is to please take a look at packet number 9. We'll go through the highlights of it. I'll try to guide you through the basics of it. Please read chapter 6. Then also chapter 10, we're going to see how we want to use it. So there's a practical use for this. We're going to actually heat up pieces of material by pumping them through electricity. And then we're going to see exactly what happens to a piece of material that in fact starts to get heated up through this electromagnetic process. So I'm going to stop here, but I'm happy to entertain questions, or we can call it a day. So Brian, if you have any announcements or anything, I'm happy to discuss anything as well. So the floor is yours, everybody, if you'd like to ask some questions. Well, then, Brian, let's call it a day, and I will see all of you on Tuesday.